Hello again, hackers. In the last few lessons, we turned an innocent-looking input into control of a program. First, the bytes escaped a buffer. Then they crossed the stack, replaced the save return address, and sent the processor somewhere the original programmer never selected. With shellcode, that destination was our own data. With Rob, it was a chain of instructions already inside the executable. Our earlier targets were intentionally generous. The stack could execute. The executable lived at predictable addresses. No secret value got, linker data remained writable. That was not a mistake in the lessons, stripping away defenses. Let us isolate one exploit primitive at a but it also gave us a distorted idea of what a contemporary Linux binary normally looks like. So, today, we reverse perspectives, we keep the memory bug, then add the defenses one at a time, and observe exactly what changes, from source code to ELF metadata to disassembly to the live process map, and one historical warning. These defenses did not all emerge from one neat sequence of famous papers. StackGuard has a canonical research paper, Hacks developed executable space protection and ASLR through implementation documents. PIE and RelRo grew through compiler. We will show those primary artifacts honestly before discussing a single instruction. Here is the complete laboratory. It contains 5 small source files, 1 reproducible build script, 1 capture script, 13 binaries, and the raw outputs used throughout this video. We are not beginning from a cropped instruction or a tidy diagram. We are beginning from the files that produced every later claim. This capture was made on 64-bit Linux with GCC 14.2 and GNU binutils 2.44. Kernel address randomization is set to mode 2. We do not disable ASLR for convenient screenshots, and we do not invent addresses that remain stable across reruns. When this lab is captured again, several pointers and process IDs should change. That change is evidence, not an inconvenience. This is the complete vulnerable program. There is no hidden helper and no omitted cleanup path. Greet reserves 32 bytes for name, then passes that address to read while requesting as many as 128 bytes. Main disables output buffering only so the runtime evidence appears in a predictable order. Every protected variant begins with the same source. When we build the variants, GCC warns us before the program ever runs. The warning is unusually direct. Read may write 128 bytes into an object of size 32. That warning is not NX, a Canary, ASLR, PIE, or RelRo. It identifies the defect. The mitigations we study later only constrain what can happen after the defective write is allowed to exist. The build produces real EL files with distinct build IDs and hashes. File identifies which are ordinary executables and which are positioned. We record those identities because later screenshots must point back to the exact artifact that generated them. A clean diagram is useful only after the evidence chaining. Before drawing a stack frame, we ask the binary what GCC actually emitted. The disassembler interleaves the full source with the machine instructions for greet. The disassembler shows greet beginning at its recorded address. It reserves 48 bytes, places the buffer at RBP-48, asks read for 128 bytes, then reaches leave and ret without an integrity check. Now the diagram has a provenance. Sub RSPI's 30x30 gives the local frame area. REPP-SORX30 locates the saved frame pointer and return address sit above the current frame. This is still a reconstruction. We did not dump every stack byte, but its distances are derived from the instructions we just inspected, not from a generic textbook layout. To isolate execute permission, we use a second complete program. Its local array contains 6INS86 64 bytes. Move EX, the program prints the array's address, casts that address to a function pointer, and calls it. The 2 binaries are identical except for the linker stack execution request. This is safer and clearer than asking a full shell payload to prove several things at once. First, we inspect the ELF program headers, not a handwritten permission card. In the executable stack build, the GNU stack row ends in RWE, read, write, execute. In the protected build, the same row ends in RW, read and write, with execute absent. The close-up only appears after the complete header table has established where that row came from. Now, we run both artifacts. With the executable stack, the program prints its stack buffer, calls those bytes, and returns 42 with status 0. With NX, the same call is terminated by signal 11 and the shell reports status 139. The bytes were accepted as data in both cases. The difference appears only when the CPU tries to fetch instructions from that page. The wider idea is executable, space protection. PAX developed PAGI-XC and related mechanisms for systems where convenient hardware support was not, and its documents describe making stacks, heaps, and anonymous mappings non-executable, while reserving execution for mappings that contain code. MX is not a detector looking for suspicious byte patterns. It is permission enforcement. The write into the array succeeds because the stack is writable. The indirect call also succeeds in changing RIP because NX is not control flow integrity. Failure occurs at the next stage, instruction fetch. The translation and permission machinery sees an address in a page without execute permission, so no instruction from B8 reaches the decoder. The data survives, execution does not begin. This is why ROP was the next logical technique. The corrupted stack supplies data, addresses, and values, while instruct and X remove the assumption that writable bytes could also be instructions. It did not remove the overflow, stop ret, or erase the program's own executable code. One attack route closed, another remained. To see what stack protection changes, we compare the complete read functions. The unprotected version reserves 0x30 bytes, and the protected version reserves 0x40, loads a value from fs:0x28, stores it at RBP-8, performs the same vulnerable read, then reloads and compares that saved value before leave and ret. The disassembly tells us where the compiler reads and stores the guard, but we can also measure the values. This architecture-specific probe reads the x86-64 thread local guard from fs:0x28 and the compiler's frame copy from RBP-, then prints both. It is instrumentation for this lab, not portable application code, and its complete source remains on screen before we inspect the numbers. Across 3 executions, the guard changes. In each execution, however, the thread local guard and the frame copy are identical. The second prints 897.000, the third prints 5B33 through 1800. We are not choosing aesthetically convenient values. These are the values. In 1998, Crispin Cowan and his co-authors presented StatGuard. Their paper places a canary word between local data and the return address, then verifies it before the function returns. Its figure 2 is not merely decorative history, it gives us a primary source-stack relationship to compare with the compiler output we just measured. At function entry, the protected binary reserves 64 bytes. Instruction 0x4E116E copies the thread local guard into racks. Instruction 0x, the buffer begins at RBP-0x30. That puts the canary above the buffer in the path towards saved frame data. The diagram is a reconstruction, but every distance shown comes from the selected instructions. The canary does not stop the write. The first 32 bytes occupy the declared array. More bytes continue through adjacent frame storage. Eventually, the stream overwrites the saved guard, then can continue towards saved RBP and the return address. The defensive stack protection records that corruption now, so it can react before control is returned later. The epilogue reloads the protected value, compares it with the current thread local guard, and takes the failure path unless they are equal. If they differ, the stack check failure routine runs. Only after the equality check do leave and ret execute. The corrupted return address can exist in memory and still never reach RIP. With 96 filler characters, the unprotected program reports a 96-byte read, then exits with signal 11 and status 139. The second program reads the same amount, reports stack smashing detected, then exits with signal 6 and status 134. One crash happens after corrupted control flows, the other detects corruption before return. A stack canary is therefore a tamper check for particular protected frames, not a universal memory safety system. It does not repair read, protect every heap object, or make all pointer corruption impossible, and if another bug reveals the current guard, an attacker may reproduce that value while overwriting data around it. The next defenses also rely on hidden values, and that makes disclosure our recurring enemy. To observe address randomization, we use another complete program. It prints its process ID, the address of main, one local stack variable, a reference to puts, and the actual libc implementation found with dlsim. If launched with hold, it waits so we can inspect proc while that exact process is still alive. The kernel reports randomization mode 2 across 4 runs of the non-position independent build. The program main function and its linked puts reference remain fixed. The local stack pointer, the actual C library puts address changes every time. This is the first important separation. Address randomization is active, but an ordinary non-positioned independent main executable can still provide fixed addresses. This is the actual map for that held process. The executable begins at its recorded fixed base, and its executable page is the next mapping. The C library file mapping appears at a randomized high address, and the user stack occupies another randomized high address range. We show the whole map first because a selected row without its process and file context is easy to misread. The facts. ASLR design states the central objective plainly. Introduce randomness into addresses so attacks requiring It also states the central weakness. If the process can disclose its randomized layout, guessing is no longer necessary. The protection is not that the addresses cease to exist, it is that their current values become secret process state. ASLR does not normally throw every function into an independent random slot. It randomizes the base of mappings or regions. In one particular libc build, puts remains at a fixed offset from the library's base. When the library moves, the base and puts move together. The preserved internal distance is precisely what later allows one leaked pointer to reveal the whole region. Captured runtime metadata tells us where this program loaded its C library. The resolver's puts address, minus its file offset, reproduces the current run's library base. Those numeric values are specific to this build, and one run. The relationship runtime address equals base plus known offset is reusable. Address randomization was also studied as a broader compiler and loader strategy. Bhatkar, Duvernay, and Sekar described address obfuscation across code. Shacham and colleagues later evaluated the practical limits of ASLR in a 32-bit setting, where restricted entropy and repeated attempts mattered greatly. The correct lesson is neither ASLR solves exploitation, nor ASLR is useless. Its strength depends on entropy, restart behavior, and especially information disclosure. When a program reveals a pointer into libc, the attacker no longer needs to guess that run's base. Subtract the known offset of the revealed object, and the randomized base becomes measurable. ASLR has not been switched off. It's hidden, that is the ASLR part of ret to libc, but before we can use the main executable to perform such a leak, we must ask whether the executable itself is fixed. The file inspection makes a distinction before the program runs. The non-position independent build is a fixed executable. Its main function has one linked address. The position independent build is dynamically loaded. Its main value is an offset, not a permanent location. The full headers and symbol tape PIE and ASLR are related but not synonymous. PIE is the property that lets the executable operate at different bases. ASLR is the runtime policy that selects a base for a particular execution. A relocatable executable can be placed somewhere new. A fixed address executable still expects its linked home. Only the combination gives us a randomized main binary. Across 4 position-independent runs, the same main code, stack, and C library all move to different runtime bases. The printed puts reference moves with the executable's own code address is no longer a stable island across runs. For one captured run, the position-independent executable begins at a recorded load base. The main function has a known file offset. Base plus offset reproduces its current runtime address. Position independence changes absolute addresses but preserves offsets inside this build. Just as randomization preserves offsets inside the C level without PIE, fixed addresses in the main binary can provide a PLT call, a GOT location, a re-entry point, or a ROP gadget even while libc moves. With PIE, those objects move together with the executable. An exploit often needs a binary pointerly before using them reliably, but PIE does not erase the objects, change the internal offsets on every launch, fix the overflow, or conceal a pointer that the program itself prints. To observe dynamic binding order, we use a fault-complete program. It writes explicit markers to standard error before and after the first call to puts, then sleeps so its mappings can be inspected. 3. Non-P. IE binaries are built from this source: no rel row with lazy binding, partial rel row with lazy binding, and full rel row with immediate binding. Relocation protection cannot be inferred from one green label. We compare program headers, dynamic tags, relocation records, and section headers. The unprotected file has no protected relocation segment. Partial protection has a protected range but no immediate binding flag. Full protection has a larger protected range and requests immediate binding. Then we connect each file relocation record to a live memory page. In the unprotected and partially protected examples, the puts relocation falls inside a writable. In the fully protected example, it lies on a read-only page. That permission difference is the observable result. To see when symbols are resolved, we ask the dynamic loader for binding diagnostics. The raw output is dense, more than 100 lines, because the loader reports findings for the executable, libc, and the loader itself. We show that complete stream first. Only then do we select the lines around transferring control, our program markers, and the bindings for write, puts, and sleep. In the partial build, the loader transfers control to the program first. Write is bound as the first marker runs. The program announces that it is before its first puts. Only then does the loader bind puts. Sleep is bound later as well. Lazy binding postpones these writes until the corresponding call path is used, which is why the procedure linkage slot must remain writable during normal execution. In the full build, the order reverses. The loader binds puts, write, and sleep before the line that transfers control to the executable. Only afterward do our entered main and before first puts markers appear. Because the required procedure linkage writes are completed during startup, the page containing puts can be read only by the time ordinary program code runs. Draper's engineering report explains the layout problem behind rel row. Some ELF structures must be writable while relocations are performed, but should not remain writable afterward. The report's own diagrams show protected ELF data reordered next to read only data so the loader can cover it with a read-only page range after relocation. Full rel row combines that layout with immediate binding. The conceptual calling path is now safe to animate, because we have already located its real relocation entries and binding events. A call reaches the PLT root. The root consults the relevant GOT slot. Before resolution, that root can enter the dynamic resolver. After resolution, the slot contains the libc destination. Partial rel row permits later. Loader writes for lazy binding. Full rel row resolves first, then removes write permission. Full rel row blocks writes to the protected relocation page. It does not make the page unreadable. The mapping we measured is RP, not inaccessible. A disclosure primitive may still read the resolved puts pointer, and that pointer can still reveal libc's randomized base. Rel row closes the it does not close code, reuse, information leakage, or corruption of unrelated writable objects. Only now, do we compress the evidence into a summary. NX comes from stack execution metadata and page enforcement. The Canary appears as compiler-generated prologue and epilogue instructions. ASLR appears in changing runtime mappings. PIE changes the ELF type and lets the main binary receive a randomized base. RelRow combines ELF layout, binding policy, and loader enforced read. The source level defect never changed. 32 bytes of storage, 128 bytes requested. What changed was the point at which an exploit's assumptions failed. NX waits until instruction fetch. The Canary reacts before ret. A ASLR invalidates yesterday's runtime pointer. PIE removes fixed main binary addresses. Full RelRow rejects a write to the relocation page. No single layer is the final answer. ROP can root around NX. A pointer disclosure can reveal an ASLR base. A leaked Canary can preserve the stack check. A leaked code pointer can reveal a PIE base. Full RelRow can force an attacker away from GOT overwrites without preventing every code reuse path. Defense in depth works by making a successful chain require several independent capabilities in the same vulnerable process. Return once more to the compiler warning. It identified the actual engineering failure before any mitigation activated. NX did not reduce the requested length. The Canary did not make the destination larger. ASLR and PIE did not validate the pointer. RelRow did not constrain read. A corrected bound, a memory-safe abstraction, or a design that cannot express this mismatch addresses the bug itself. The protections reduce exploitability, and now ret to libc stops looking like a bag of arbitrary tricks. NX explains why we reuse executable code instead of running bytes from the stack. ASLR explains why libc's base must be learned. PIE explains why even our PLT entries, GOT locations, and gadgets may require a binary base leak. The Canary explains why a blind overflow can die before ret. RelRow explains why reading a GOT entry may remain useful even when overwriting it is blocked. Today we did not begin with 5 floating shields and assign them magical powers. We followed real source into real binaries, inspected their headers and instructions, ran them, read their live mappings, and then built the diagrams from that evidence. The result is a defender's map of exploitation, executable permission, stack integrity, randomized placement, relocatable code, and hardened. Next time, we ask what happens when the program leaks the map.